In this hour, we will talk about superposition in S domain. Okay, so let's quickly remember what linearity allowed us to do for LTI resistive circuits. Okay, so for an LTI resistive circuit, we are allowed to do the following. Okay, so we have y equals k1. Okay, so we're in time domain, so let me write as follows: y of t equals k1 w1 of t plus k2 w2 of t kn w n of t. Okay, so where y is any output, meaning any branch current or voltage that somehow we're interested in. Okay, this is any output of the circuit. Okay, and these WIs, they are the currents and voltages of the independent sources. Okay, and those we call the inputs. Okay, so inputs of the circuit. Okay, namely the independent, the voltages of the independent voltage sources and the currents of the independent current sources. And Ki are the weighing factors. Okay, that depend on the circuit. Okay, and they are, for an LTI resistive circuit, they are constants. Okay, and here, okay, so the inputs are the independent voltage or current sources. Okay, now, and this property, this linearity property, allowed us to apply or to use the principle of superposition, which, for instance, through which we can, for instance, kill all the sources, let's say from W2 to Wn, and figure out the component of the output due to the first source. Okay, and then what we do is we let W2 be active and then kill all the sources, and we figure out the component that's due to W2 only, and that would be K2 times W2, and then we do that for each independent source, and then in the end, since the circuit is LTI, we can collect all those n terms and write the output. Okay, and that we call superposition. Now, this property is valid also for circuits in S domain. Okay, so the superposition, okay, this property is valid in S domain, okay, for LTI dynamic circuits. With the difference that the weighing factors here, okay, now for LTI resistive circuits, they are constants. Now the weighing factors are rational functions of S, namely some numerator polynomial of S divided by some denominator polynomial of S. Okay, that the weighing factors are rational functions S, okay, rather than constants. Okay. So that's one difference. There's also a subtlety regarding what to consider the input in S domain, and it's this. Also, in the S domain, there are two types of independent sources. Independent sources, and we're already familiar with that fact. First, of course, we have independent sources in S domain that are representing the independent sources in the time domain, okay? But there are also some independent sources in S domain which are representing the initial conditions in our dynamic components, okay? Namely, the initial capacitor voltage and initial inductor current. Okay, so we have therefore two types: voltage, current sources representing the independent sources in the time domain. Those we're going to call external driving forces. Okay, a little informally. And the second type is the type that represents the initial stored energy in our dynamic components. Okay, type 2 voltage current sources representing the energy stored at the initial time at t equals 0. Okay, so that's due to non-zero initial conditions. And then the overall response clearly is due both to 1 and 2. Okay. The overall response, or the complete response, is due both types of independent sources, both to 1 and 2. Now, if we kill the sources that belong to type 2, okay, so that's if we assume that for all the initial conditions to be 0 and compute the response due only to inputs of type 1, then what we obtain is 0 state response. Okay, it's 0 state response because we're killing these sources, and these sources are representing initial conditions. And then if we kill the sources of type 1 and figure out the response due only to the sources of type 2, then what we figure out, what we obtain is the so-called 0 input response. Okay, so you kill the input and then you figure out the response due to the initial conditions only. And then circle is linear, therefore we can combine those two pieces, put together, and what we will have obtained is the complete response, or the overall response. Okay, so let's put that down. If we kill the sources that belong to the second group, the component we compute is zero state response. Okay, zero state meaning all the initial conditions are set to zero. And if you do the reverse thing, when group 1 is killed, then we obtain zero input response. We obtain and the sum. So we are allowed to superpose those two separate answers because the circuit is linear. The sum of those two individual responses will provide us the overall response or the complete response. Okay, the sum of these components gives us the overall response. Okay, now let's apply this principle on a simple example. Okay, so here is the circuit, and we're told that the circuit has reached steady state at t equals 0 minus, and at t equals 0 a switch closes, and that produces a response, and we're asked to figure out that response. Okay, now this is the circuit. Okay, we have a constant current source, we have an inductor, a resistor, and a capacitor. Okay, everything is parallel to one another, and we are asked to figure out this voltage V of t, R, C, L, and here we have a switch which closes at t equals 0. As for the source, the current source, Is of t equals some constant which we denote by I1. So this is, okay, this is a constant source. Okay, so it's a DC source, and therefore the steady state we're talking about is the DC steady state. Okay, so therefore in steady state what we have is, first of all, since this switch is open for negative times, the inductor current is always 0. Okay, I told for all negative times, and then the circuit has reached steady state, in which DC steady state, in which capacitor behaves like an open circuit. So this is open circuit, this also is open circuit because the switch is open. So that means all the current is flowing over the resistor. So that generates the voltage I1 times R, and that I1 times R will be our initial capacitor voltage. Okay, so initial capacitor voltage will be I1 times R, and initial inductor current is clearly 0. And then using that set of initial conditions, and here we have the input, we will try to figure out the response V of t, this voltage, capacitor voltage, or, well, anything's voltage. Okay, so this is what we are asked to find: the zero state and 0 input components of the voltage V in S domain. Okay, so of V of S. And part B is the numerical part. Find the voltage in time domain V of t for the following numbers. Okay, I1 is 1 milliamp. The inductance is 2 Henry. The resistance is 3/2 kilo ohms. The capacitance is 1/6 microfarads. Okay, and we have to figure out V of t for those numerical values for after the switch is closed, for t greater than or equal to 0. Okay, so let's begin our solution. And the first step is, since we asked for V of S, the first step is transforming the circuit to S domain. Okay, so here is the solution. A. The S domain circuit reads as follows. So we have the current source, we have the inductor, okay, we have the resistor, and finally we have the capacitor. Okay, now since inductor inductor current is 0, okay, therefore the inductor in time domain will be represented only by its impedance. Okay, so there will be no independent sources associated to the initial condition of the inductor in S domain, because the initial inductor current is 0. And the impedance, so it's only represented by its impedance, and we know that that impedance is S times the inductance, SL. And then as for the resistor, we directly carry it to S domain. Resistance here is R, therefore resistance here is R. Okay. And as for the capacitor, it will be represented by its impedance plus, because it has non-zero initial condition, plus an independent source. Okay, a voltage source or a current source that represents its initial condition. Okay, so what we have therefore is, for the capacitor, the impedance of the capacitor and a voltage source, independent voltage source, for instance, that would represent its initial condition, which is I1 times R. Okay, so the impedance of the capacitor is 1/SC. So here the units are Henrys, let's say Henrys or millihenry something, Henry, ohm, and farads. Now everything is in ohms, ohm, ohm, ohm. Okay. Now, how about these sources? As for this source, it's constant, I1, in time domain. Therefore, in S domain, it's the Laplace transform of a constant, and the Laplace transform of a constant is that constant divided by S. So here, I1/S is the S domain representation of this constant time domain signal. As for the voltage of the capacitor, the voltage source here, which represents the initial condition of the capacitor, it simply equals V0, V0 being the initial condition, initial voltage of the capacitor, V0/S. Now here the V0 is I1 times R, because the circuit is said to have reached steady state. So that means here we have I1 times R/S. Okay. And this voltage here that appears is our V of S, the S domain circuit. Okay, now let's, for simplicity of analysis, let's apply source transformation to this pair of impedance connected in series with that voltage source, and represent that by an impedance connected in parallel with a current source, so that the circuit becomes a little bit easier to analyze. Okay, so if we apply source transformation to this, what we have is the impedance will be 1 over SC, and then the current, that's the current of the current source that will be parallel to that, will be, in a sense, Thevenin voltage divided by Thevenin impedance. Okay, I1R over S divided by 1 over SC, that produces I1RC. So after that transformation, we have the following equivalent circuit. And here, this is our voltage that we're looking for. Okay, this is I1 over S. And here we have SL. Here we have our resistor, R. And then this is our impedance, 1 over SC for the capacitor. And now the initial condition of the capacitor is being represented by a current source instead of a voltage source. And that current source has current that equals capacitance times the initial voltage, CV0. Initial voltage is I1 times R. Therefore, here we have I1R times C. Okay. Now all the sources are current sources in our circuit, or all the inputs are current sources. And we can easily classify those inputs. Now this input is representing this input here, okay? Therefore, it's representing the external driving force, whereas this input, or this source, which is another way, which is representing this source, and this source is representing the initial condition of the capacitor. Okay. Therefore, this is representing the initial conditions. This is representing the external driving forces. So, if we kill this source and figure out the response due to that, we will have computed zero input response. And if you do the reverse thing, we will have computed the zero state response. Okay. And to help in our computations, a nice middle step seems to replace that bank of inductor or bank of 3 impedances by an equivalent impedance. Okay, so let's therefore in our next step figure out the equivalent impedance for that for these 3 parallel components. Now Z equivalent equals 1 over the equivalent admittance. Okay, equivalent impedance equals 1 over the equivalent admittance, and equivalent admittance is, since we have parallel connections, simply is the sum of individual admittances. This is the impedance. Admittance is 1 over SL. The admittance is 1 over R, and here the admittance is 1 over SC, which is SC. Okay, so we have 1 over SL plus 1 over R plus SC. Okay, this is the sum of admittances, which is equivalent admittance. 1 over the equivalent admittance gives us equivalent impedance, and that can be simplified into 1 over CS over S squared plus 1 over RC S plus 1 over LC. Okay, so that's the equivalent impedance. And now what we have is 2 current sources, and parallel to those 2 current sources we have the equivalent impedance. So let's therefore redraw the simplified version for our circuit. We have this topology now, okay? And we are after this voltage, okay? V of S. This is our Z equivalent, which we just computed. This is I1 over S, okay? This source, and this is the source that represents the initial condition of the capacitor, okay? Which is CV0, V0 being I1 times R, we have I1 RC. I1 RC, okay? So, okay, let's make it clear. This represents the external inputs. And here, this guy represents the initial conditions. Okay. Note that we didn't have a source representing the initial condition of the inductor because initial inductor current was 0. Okay, so therefore the inductor is represented only by its impedance, S times L. Okay, now everything is easy to see in this simplified circuit, and we can therefore write easily V zero state response equals Z equivalent S times, what you do is, this is zero state, therefore you kill the initial condition. You kill the initial conditions, so that would mean you're killing this source, okay? Only this source is active. This is open circuit because killing a current source means replacing it with an open circuit. And this is the only active source, and all the current clearly flows over Z equivalent, okay? And that produces the voltage which equals Z equivalent times this current. So what we have is Z equivalent times I1 over S, and that reads okay, that reads I1 over C S squared plus 1 over RCS plus 1 over LC. Okay, so let me squeeze here also the zero input response and the zero input. Okay, the zero input response is Z equivalent of S times, since we're dealing with zero input, what we do is we kill the external driving forces, therefore we kill this source, the only remaining source is this, and that generates voltage that equals Z equivalent times this current, I1 RC. I1 RC, and that equals I1 RS over S squared plus 1 over RCS plus 1 over LC. Okay, and hence, since superposition principle is valid in S domain, by combining these two pieces, or summing those two pieces, zero input and zero state, we obtain the overall response, okay, V of S, when everything is considered at once. Okay, so that implies the following. So the final answer, therefore, is V of S equals VZS, the zero state response, plus VZIS, the zero input response. Okay, so we can superpose those two separate components and obtain the overall or complete response. And the complete response reads as I1 R S plus I1 over C S squared plus 1 over RCS plus 1 over LC. Okay, so that completes part A. let's now figure out in part B the numerical value of v of t for the given values of certain quantities. Okay, now VZS of S for the given values in the question produces the following: 6,000 S squared plus 4,000 S plus 3 million, okay? And that can be written as 6,000 over S plus 1,000 times S plus 3,000, which can be written as something over S plus 1,000 plus something over S plus 3,000, and those somethings, what we're calling the residues. The residue for the pole minus 1,000 is 3, and the residue for the other pole at minus 3,000 turns out to be minus 3. So what we have is therefore minus 3 here. Okay. And once zero state response is written in that form, that is this, the sum of first order terms, we can easily write down the time domain signal, okay, corresponding to that function in S domain. So that produces VZST. So that's the zero state component of the voltage in time domain, simply equals 3 times e to the minus 1,000 t minus 3 times e to the minus 3,000 t for t greater than or equal to 0. Okay, so that's 3 e to the minus 1,000 t minus 3 e to the minus 3,000 t volts. Okay, for t greater than or equal to 0. So that's the zero state component. As for the zero input component, let's also do that. Okay, zero input response in S domain reads 1.5 S over S plus 1,000 times S plus 3,000. Again, that can be written as sum of first order terms, and that produces minus 3 over 4 S plus 1,000 plus 9 over 4 S plus 3,000. Okay, which means in time domain we will have minus 3 over 4 e to the minus 1,000 t plus 9 over 4 e to the minus 3,000 t volts. Okay, for t greater than or equal to 0. Okay, 4 times after the switch is closed. And finally, thanks to linearity of the circuit, superposition is valid, and the overall response v of t equals v zero state plus v zero input. Okay. Now, in our second example, we will deal with again a second order circuit. Here is our example. We have a constant source and it's connected to the following circuit: 1 farad, 1 ohm, 1 Henry, 1 ohm. So all the units, all the values are of unity, and we have a 4 volt source, constant source, and this is the capacitor voltage, this is the inductor current, IL. Initial conditions are given as 2 amps for the inductor current and 1 volt for the capacitor voltage. And we're asked to find VCT, okay, for T positive. Okay, so let's solve this using S-domain techniques. That is, the first step will be transforming this circuit to S-domain. And then once that's done, that circuit behaves just like, the S-domain circuit behaves just like an LTI resistive circuit. These Henrys and Farads, they become ohms, okay? So everything in terms of ohms. And then it's very easy to figure out whatever we're asked to figure out, okay? We don't have to solve any differential equations. And once we have VC of S, S-domain, the last step would be transforming that into the time domain by inverse Laplace transformation. Okay, so let's proceed by writing down the circuit in S-domain. Now, let's begin with this. Let's begin with the resistors. Resistors directly carry to S-domain, okay? 1 ohm, 1 ohm, and they are here both represented by 1 ohm resistors, okay? As for the source, what we do is you take this Vs of t and transform to the S-domain Vs of S. Now, Vs of t is constant, therefore, its Laplace transform is that constant divided by S. So we have here 4 over S volts. Okay. Now this inductor is represented by an impedance and a source corresponding to its initial condition, okay, which is 2 amps. So the impedance is S times L, L being the inductance. In this case, L is 1. So the impedance of our inductor is S ohms. Okay. As for the initial condition, it can be represented by a current source that's parallel to this impedance, and if you do that, then the current of this current source is initial inductor current divided by S. Now, initial inductor current is 2, therefore this should be 2 over S amps. Okay. Now, as for the capacitor, it's represented by an impedance and a source, independent source, that corresponds to the initial condition. The impedance of the capacitor is 1 over SC. C is 1, therefore we have 1 over S ohms for the impedance. And the voltage of the voltage source, the dual of this case, is initial condition divided by S. Now, initial voltage is 1, so this will be 1 over S volts. Okay. Now, in this representation, what's the capacitor voltage and what's the inductor current? Sometimes it's a common mistake to mark the capacitor voltage in S-domain circuit as simply the voltage drop across the terminals of this impedance, because here this looks like a capacitor. And here we have the same symbol, but capacitor here in time domain is not represented only by this impedance, but this impedance plus this voltage source representing the initial condition. Therefore, the Vc of S, the Laplace transform of the capacitor voltage, is the voltage drop across the terminals of these two components considered together. So this is Vc of S. Okay. Similarly, the inductor current or IL of S is not the current passing through this impedance, but that current plus the current of the source representing the initial condition. Therefore, inductor current will be the current passing through this 1 ohm resistor in this circuit. Okay. Now, we're going to solve this circuit, treating just like an LTI resistive circuit, and so we have many methods. We can use node analysis, mesh analysis. So we already used node analysis in one of our previous examples. So for this case, let's apply the mesh analysis. But for that, let's reduce the number of meshes by applying source transformation to this pair, the impedance and the current source. And if you do that, we will have only two inner meshes. Okay, so let's do that. That circuit is equivalent to the following one. S ohms, 1 over S volts, S ohms minus plus 2 volts, 1 ohm, and this is 4 over S volts. Okay, so what we did is we apply source transformation to this component, to this parallel combination here, and we obtain this impedance connected in series with a voltage source. By doing that, we reduce the number of meshes, and now we can apply mesh analysis. So let this be our first mesh current, and let this be the second mesh current, I1 and I2. Okay, what we're asked for is Vc of t. So how we can proceed is, in this circuit, we write down the mesh equations and solve for I2 of S. And once we have that current, okay, I2 of S, the current flowing over the capacitor voltage, Vc of S, simply is that current I2 of S times this impedance 1 over S plus this voltage 1 over S. Okay, and those two voltages together produces Vc of S. And once we have Vc of S, we can compute its inverse Laplace transform and write down Vc of t. Okay, so let's proceed. Loop 1, or the mesh 1. Starting from here, we have minus 4 over S. Okay, plus this voltage, 1 times I1. Okay, and then we are here, plus S times I1 minus I2. And then we have minus 2. Then we have this voltage, which is 1 times I1 minus I2, and that's it for the first mesh. And by KVL, which holds in S domain, this must equal 0. Okay, and this reorganized reads 2 plus S I1 minus S plus 1 I2 equals 2 plus 4 over S. So that's our first equation, first mesh equation. Let's call it equation number 1. Let's do the same thing for the second mesh. Okay, starting from this point and going clockwise, we have one times I2 minus I1, then we have the voltage of the voltage source, 2 volts, then we have plus S times I2 minus I1, and then we are here plus 1 over S times I2, and finally plus 1 over S. Okay, the voltage of the voltage source, and that equals 0. Reorganizing that equation produces minus S plus 1 I1 plus S plus 1 plus 1 over S I2, and the right hand side is minus 2 minus 1 over S. So that's our equation 2. Okay, 2 equations, 2 unknowns, and we can figure out easily I2 of S. So let's do that. Now, combining equations 1 and 2 and put them in a single equation, we obtain the following. Some matrix with entries, rational functions of S, times the vector of unknowns, namely the mesh currents, equals the vector that collects the right-hand side. Okay, so here this is I1 of S and this is I2 of S. For the first row, we look at the first equation. Here we have 2 plus S. Okay, S plus 2. And here we have, okay, the first equation, right, minus S plus 1. Okay, minus S plus 1. And the right-hand side is 2 plus 4 over S. 2 plus 4 over S. For the second row, we look at the second equation, which is minus S plus 1. And here we have a second order term, S squared plus S plus 1 over S. And right hand side is minus 2 minus 1 over S. Okay. Now, note that this matrix here multiplying our vector of unknowns, namely the mesh currents, is the S-domain representation of our mesh impedance matrix in time domain. Okay, so this is the mesh impedance matrix in S-domain, and the roots of its determinant, we know, gives us the natural frequencies of the circuit. So let the determinant of this matrix be delta of S, okay? And let's put this remark here. If you compute this determinant, you will obtain something, some polynomial dividing some other polynomial, and you take the numerator polynomial, roots of that numerator polynomial, which also can be called the roots of the determinant, okay? Or the zeros of the determinant are the natural frequencies of the circuit, okay? So natural frequencies of circuit are the roots of the determinant function. Okay. So let's compute this determinant. This times that minus this times that. Okay. S plus 2 times S squared plus S plus 1 over S minus minus S plus 1's square. Okay, and that reads S squared plus 2S plus 2 over S. Okay, and then this is the numerator polynomial. You figure out its roots, and the roots are the natural frequencies of the circuit. And the roots turn out to be -1 plus -j, a complex conjugate pair. Therefore, the natural frequencies of our circuit are S12 equals -1 plus -j. Okay. Now, let's proceed with our solution. And having obtained the determinant, we can easily inverse that matrix and write I1, I2 equals the inverse of the mesh impedance matrix times the right-hand side, which is this vector here. The inverse of the mesh impedance matrix is 1 over the determinant, which is S over S squared plus 2S plus 2 times the adjoint or adjugate matrix. What we do is we just replace, we swap the diagonal terms. So here we have S squared plus S plus 1 over S, and here we have S plus 2. And then we negate the anti-diagonal terms. So here we have S plus 1, and here we have another S plus 1. Okay. Now, times the right-hand side. Okay, so this here is the inverse of our mesh impedance matrix in S domain, times 2 plus 4 over S and minus 2 minus 1 over S. Okay. From this, we can figure out I2, which is determinant, 1 over the determinant, times the second row, times the right-hand side vector. Okay. And then once we have I2, I2 times this impedance 1 over S plus this voltage 1 over S produces Vc of S. So we will have obtained Vc of S, and then by computing its inverse Laplace transform, we figure out Vc of T. Okay. So computing I2 and simplifying the expression, we obtain I2 of S as S plus 2 over S squared plus 2S plus 2. Okay, and then that produces Vc of S equals I2 times the impedance of the capacitor, okay, plus the voltage of the voltage source that represents the initial condition of the capacitor. So that means 1 over S, I2 of S, plus the voltage 1 over S. And that equals S squared plus 3S plus 4 over S times S squared plus 2S plus 2. Okay, and that can be written as S squared plus 3S plus 4 S times S plus 1 plus J, S plus 1 minus J. Okay, because the roots of this polynomial are at minus 1 plus minus J. And by looking at the roots of the denominator polynomial, we can see the form of Vc of T. Now this will produce a constant term, okay, and this pair will produce e to the minus t times cosine t and sine t terms, okay. So this will produce a constant term, and these pair produce e to the minus t cosine t and e to the minus t sine t terms. Okay. Now, so that means Vc of S can be written as something divided by S, so that's the residue corresponding to the term at S equals 0, plus something times the sine term plus something times the cosine term, or cosine and sine term. Okay, so here we have s plus 1 square plus 1 square, okay, s plus alpha square plus omega square, and here we have s plus 1 also. So this will produce e to the minus t cosine t term, and as for the sine, we have the same denominator plus 1 square, and here we have omega, okay, and omega is 1 in our case, so we put a 1 here. Okay, so let's figure out K1, A, and B. And then once we have that, the answer will be K1, BC of t. Okay, the time domain answer will be K1 plus A times e to the minus t cosine t plus B times e to the minus t sine t. Now K1 is easy to compute. You multiply both sides with S, okay, this is VC of S, and then evaluate what remains at S equals 0. So K1 equals S times VC of S evaluated at S equals 0, and that produces 2. As for A and B, we can do the following: 2 over S. Now K1 is known. Okay, plus A times S plus 1, S plus 1 square plus 1, plus B times 1 over S plus 1 square plus 1 equals, now this is VC of S, and VC of S is here as a single piece, so that equals S square plus 3S plus 4 over S times S squared plus 2S plus 2, okay? Now, write this as a single fraction, okay? And then equate the numerator polynomial, the coefficients of the numerator polynomial, and then you will have enough many equations to figure out A and B. And that produces A equals minus 1 and B equals 0. Okay, so now we know K1, A, and B. We can write the final answer. Okay, so VC of S therefore equals 2 over S minus S plus 1, S plus 1 squared plus 1. Okay, and that means VC of t equals the inverse Laplace transform of this guy, which is 2, minus the inverse Laplace transform of this guy, which is e to the minus t cosine t volts. Okay, for t greater than or equal to 0.